Hi students, welcome to the video module on the reflection of electromagnetic waves at a conducting surface. In the previous modules, we learned about a reflection of electromagnetic waves at dielectric boundaries. The boundary conditions that we use to analyze a reflection and a refraction at an interface between two dielectric media that do not hold in the presence of free charges and currents in the case of a conductor. So, for the case of a conductor where free charges and free currents are present, we have to use the boundary conditions as shown here. Epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular equal to sigma F, where sigma F is the free surface charge and the other one is E1 parallel equal to E2 parallel and B1 perpendicular equal to B2 perpendicular, and 1 over mu1 B1 parallel minus 1 over mu2 B2 parallel equal to Kf cross N, where Kf is the free surface current and N is a unit vector perpendicular, or N is a unit vector perpendicular pointing from medium 2 to medium 1. And we know that for ohmic conductors, J is equal to sigma times E. We learned Ohm's law. So for that, we can write J equal to Jf is equal to sigma times E for ohmic conductors. And there can be no free surface current because this would require an infinite electric field at the boundary. Now, let us come to the present situation of reflection at a boundary. Just imagine that a boundary or there's an xy plane be the boundary like this. Okay? And the wave is traveling along the z axis. This is the x-axis. This is the y-axis. So boundary on one side it is a dielectric, and the other side it is a metal or a conducting surface. Okay, so on one side of the boundary it is a dielectric and the other side it is conductor. For a dielectric like air or anything can be there. On the other side it is conductor. And imagine a wave traveling from left towards right along the z direction. And it is polarized along the x direction. Okay, so once again the situation, a wave traveling along the z direction incident on a boundary between a dielectric and a conductor. So actually it is like light traveling from dielectric towards the conductor. Now, as we know, the incident wave, which consists of electric field as well as magnetic field. The incident electric field is represented by EI complex equal to E0I complex exponential I Ki Z minus omega t. X cap shows it is polarized along x direction. And the magnetic field B is equal to B0 times B0 complex times exponential I K1 Z minus omega t. B0 can be replaced by E0I divided by V1 because we learned B equal to E divided by velocity. So this is the incident wave. And the reflected wave happens in the same medium. So reflected wave is represented by ER complex equal to E0R complex exponential minus I K1 Z minus omega t x cap. And the magnetic field component BR complex equal to minus B0R complex times exponential I minus K1 Z minus omega t y cap. And B0 is replaced by 1 divided by V1 times E0R. And the transmitted wave in the second medium is given by E transmitted complex equal to E0t complex exponential I K2Z minus omega t x cap. Here we use K2 because the wave is propagating, the transmitted wave is propagating in the second medium. And the magnetic field component of transmitted wave is given by Bt complex equal to 1 divided by V2 E0 T complex exponential I K2Z minus omega t. Instead of 1 divided by V2, or V2 is omega by K2. That is why here it is K2 divided by omega. So here we mentioned the expressions for incident wave, electric and magnetic field, reflected waves, and that of transmitted wave. Now, applying the boundary conditions, at Z equal to 0, Z equal to 0 is the boundary between the dielectric and the conductor. So at Z equal to 0, the combined wave in first medium must join with the combined wave in the second medium, according to the boundary conditions that we discussed now. Since the perpendicular component of electric field is 0 on both sides, the boundary condition 1 yield sigma F equal to 0. According to the first boundary condition, sigma F will be equal to 0. And we know that the perpendicular component of magnetic field, B perpendicular, equal to 0. So the second boundary condition is also automatically satisfied. Now, for the third boundary condition to satisfy, it requires E0I incident plus E0R reflected must join with E0T on the left side. Okay. And the fourth boundary condition with Kf equal to 0, the free current equal to 0, yield. The fourth boundary condition yield. What is actually fourth boundary condition? 1 divided by mu1 B1 parallel minus 1 divided by mu2 B2 parallel equal to Kf cross n cap. Here, instead of B1 parallel, or instead of B1, what we can write? 1 divided by V times E. That is why that expression is 1 by mu 1 times E0 I divided by V1. So V1 is also there. Minus E0 R. I mean E0 B1 parallel. B has two components. One is the incident component and the reflected component, both in the same medium. So minus E0 R divided by V1. That also taken outside. Minus, what's the second component? 1 divided by mu2 times the transmitted part. That is B0T. Instead of B0T, you can write E0T divided by V. But instead of V, we can write omega by K2. That is why omega divided by K2 can be on the top by K2. Equal to 0 because there is no free current. So we got the expressions according to the boundary conditions. Now, this can be rearranged. How? E0 I complex minus E0 R complex equal to E0 T complex on the other side. And here it is mu1 V1. It will be on the numerator now. Divided by mu2 omega. And there is a K2. So this entire term, that is mu1 V1 divided by mu2 omega times K2, can be replaced by beta complex times E0T. Okay. So we have two expressions now. One is E0T plus E0R equal to E0T, and the next one is E0T minus E0R equal to beta E0T. So now this expression is similar to what we learned in the case of reflection at a dielectric boundaries. the reflection at a boundary between two dielectrics. But only thing is that here beta is not exactly similar to that of what we learned in the in that case. Here beta is also a complex uh, number. So in solving these two expressions, which are expressions? One is E0 I plus E0 R, another is E0 I minus E0 R. So simplifying these two expressions, we can solve to get the values of E0 R and E0 T in terms of E0 I, as we done in the case of reflection at dielectric boundaries. Okay, so how to solve? First, we can add these two. So you get E0 R. Now, when you add these two, you will get E0 T. So E0 T equal to 2 divided by 1 plus beta complex times E0 I. In the same way, E0 R equal to 1 minus beta complex divided by 1 plus beta complex times E0 I. So what we obtained here is the expression for reflected components of reflected and transmitted components of electric field in terms of the incident component. These results are very much similar to what we obtained in the case of reflection at dielectric boundary, but the main difference is that the beta is not exactly same as what we discussed there. Here the beta is a complex number. Beta is mu1 v1 by mu2 omega 2 k2 complex. And for a perfect conductor, it has a conductivity sigma. It is infinity. Sigma is infinity for a perfect conductor. And K2, the propagation constant K2 is also infinity for a perfect conductor. So using this, beta value will be infinity. In the case of a perfect conductor, beta will be infinity. So using that, E0R, when you substitute the value, beta is infinity, what you will get? E0R equal to, E0R is 1 minus infinity divided by 1 plus infinity times E0I. So this will become minus infinity divided by plus infinity. So that is minus. So E0R equal to minus E0I. And E0T is, it is 1 by 2 by 1 plus beta, that is actually infinity on the denominator. That will lead to a zero answer here. So in the case of a perfect conducting material, the reflection is given by E0, R is equal to negative E0I. That means there's only a reflected component, or the wave that incident on a perfect conductor completely reflects back. There is no transmitted component for this. There is no transmitted part for this. And the negative sign, so it reflects completely with a 180-degree phase shift. So this explains why excellent conducting materials make good mirrors. Good mirrors are actually made up of excellent conducting materials like silver. So how a mirror is formed? A mirror is actually formed by polishing a metal surface. But in real practice, you know that a thin coating of silver at the back of a plain glass. Actually, the glass is not the mirror. Glass is only used to hold that silver, a very thin silver coating, because we are using a very small silver coating there. So that silver coating is a reflector. We use the glass only to hold the silver. So it has nothing to do with the reflection part. Even though a part of light is being absorbed by glass, so if it is possible to make a mirror with a perfect conductor only without a glass, that will be be of better efficiency. But in normal practice, the mirrors that we use consist of glass, and we without In real practice, most of the mirrors that is available in shops are made of glass coated with the silver at the back. And as I explained here, silver the glass is only to hold the mirror silver film. Okay, so if it is possible to make a mirror made completely of a metal, then it will be of a good efficiency. And there is such a mirror available in our Aramula Kannadi that is manufactured at the place called Aramula in Kerala state, India, is one such a perfect conducting surface mirror. There is no mirror cover is used in this mirror. It is unlike the normal silvered glass mirror. This Aramula Kannadi is a metal alloy mirror or first surface mirror or front surface reflection mirror, which eliminates the secondary reflection and aberration. So, this is a front surface mirror, and I hope you know this is the one of this is the second material that got geographic index in India after Darjeeling tea. The second one to get geographic index. You can read more about Aramulla Kannadi and its origin, history, and everything in other videos. Okay. So, okay, students. So here we learned about reflection of electromagnetic waves at a conducting surface and its difference with the reflection from a dielectric boundary and one example of a conducting surface and its importance we learned here. Okay, students. Thank you.